So good morning to everyone. Good morning. Okay. So good morning. Okay. So we will start with today's class. So that means before that we have to discuss about last class, right? So can any one of you tell me what we have discussed in the last class? Can any one of you? So we have discussed related to cleavage of OH bond, right? Means R and oxygen. Bond between carbon and oxygen. That's what we have discussed in the last class. That's where we have the Lucas test, right? So what do you mean by Lucas reagent? Yes, Bharat. Very good. So that's where we have Lucas test. Yes, Janani. Carbon and oxygen bond. We were discussing about, right? Now when I am talking about Lucas test, what is the significance of Lucas test? So Lucas test can be utilized to discriminate between primary, secondary and tertiary, or to identify whether a given alcohol is primary or secondary or tertiary. Yes, Jana. So Lucas reagent is nothing but a combination of HCl and zinc chloride. It is a combination of HCl and zinc chloride. Very good. Okay. Now here what will happen? So we will be having alcohol which will get converted into alkyl halide, respective alkyl halide. So whatever R is there, same R here should be. Only thing here is reagent will be HCl and zinc chloride, right? Now when it comes to primary alcohol, so turbidity will be at bit higher temperature, right? So we have to provide the condition, then only reaction will happen. Then secondary alcohol, so turbidity will be formed, but it will be of slow rate. It will be formed slowly, right? Now when it comes to tertiary, turbidity will be fast. Turbidity will form very fast. So no need to go for high temperature and all, right? So turbidity will be bit fast. So that's where we have the different alcohols which will show different reactions. That is related to Lucas test. So wherever turbidity will be formed, immediately that shows the presence of tertiary alcohol. Now why turbidity will be formed? Turbidity will be formed due to the formation of alkyl halides, which will be less soluble or insoluble in water or solution. It is less soluble or insoluble in solution. Therefore, alkyl halide, whenever it will be formed, it will lead to the formation of turbidity. Okay. So next we have discussed about reaction between alcohol and phosphorus trichloride. Even you can talk about phosphorus pentachloride also. In P block we have discussed, right? So phosphorus pentachloride. So that's where we have RCl and H3PO3, orthophosphorus acid. If I take PCl5, it will be orthophosphoric acid, right? That is reaction with respect to PCl3. Now next we have discussed about, any one of you, next we have discussed about dehydration. Next we have discussed with respect to mechanism also. So dehydration of alcohol, right? See, whenever you are reading any concept, not only chemistry, any subject, but if you come to the chemistry, whenever you are reading something, you should be able to analyze where we have discussed this reaction, in which chapter we have discussed this reaction, and you have to write extra reaction. In your textbook, they will be giving some of the reactions, right? So along with that, you should react. You have to make reaction with some other compounds also. Same reaction only, but with some other molecules. Then only you can improve your chemistry. Otherwise, it's not possible. Anything if it is asked related to this, but not the same thing, then you will not be able to give the answer. So try to practice that. Say for example here, PCl3 is there in this topic. Many students, what they will do? They will talk about PCl3, okay, H3PO3 will be the product. Now you should correlate where we have studied. So we have studied this one in P block. Not only PCl3, in P block they have given even PCl5. So alcohol with PCl5, what will be the product? So that's how you should start correlating. Fine? So that's how you should prepare yourself. Okay? So that's what. And next one is dehydration. So that is removal of water molecule from alcohol under acidic condition. Right? So here also we have seen tertiary alcohol can be easily dehydratable, or it can be easily dehydrated. Tertiary alcohol can be easily dehydrated. What is the reason? Due to the stability of carbocation, which will be the intermediate. In the mechanism we have seen, formation of carbocation is the rate limiting step, and that will be stable when it comes to tertiary alcohol. So therefore it will easily undergo for dehydration. Then comes the secondary, and the last one will be primary. And the last one will be primary, but dehydration will be done under acidic condition. So if I take tertiary alcohol, 20% of orthophosphoric acid, 350 Kelvin, more than enough. But when it comes to secondary, so slightly we have to increase the concentration. It will be 80% and even temperature nearly 440 to 450. Now when it comes to primary, we have to use concentrated H2SO4 and approximately 450 Kelvin, 440 to 450 Kelvin, right? So that's where we have the dehydration of alcohol, where tertiary alcohol once again dominate over other alcohols. Fine? That's what we have discussed. Next one is dehydrogenation. Next we have discussed is dehydrogenation. Now when I am talking about dehydrogenation, that is removal of hydrogen from the alcohol. Removal of hydrogen from the alcohol. So that's where we have the OH, which can be converted into CHO. So which can be converted into CHO. Now, if you have taken RH, that is primary alcohol, then the product can be aldehydes, right? So we are removing the 2 hydrogen. So 1 hydrogen, 1 hydrogen. Left over is only 1 hydrogen. So that's where it will be aldehyde. But only thing here is we have to provide a mild oxidizing agent, not a strong oxidizing agent like KMnO4. Acidified KMnO4 will not going to work here. If you are using acidified KMnO4, it can lead to the formation of carboxylic acid. Sometimes it can lead to the cleavage of the bond. That's where we are going to use the mild oxidizing agent, that is CrO3, chromium trioxide. Same way, whenever we are taking secondary alcohol, so once again H, it will be removed. So leftover will be ketone. Leftover will be ketone. So what I mean to tell here is, this is an example for dehydrogenation. Now we have discussed about PCC. What do you mean by PCC? Pyridinium chlorochromate, right? So PCC is nothing but pyridinium chlorochromate. So this one you have to remember. Chromate, negative charge. Pyridinium, positive charge. That's what we have seen in the last class. So PCC, you can expect the question, right? So this was another reaction, important reaction what we have discussed. Same way, last before leaving, we have discussed about very important reaction, that is primary alcohol, secondary and tertiary alcohol in the presence of copper 573 Kelvin. It is constant for all the things. But only thing here is these two. It will give rise to aldehyde and ketones. But last one, it will go to the formation of alkenes, that is unsaturation. That's what we have seen in the last class, right? So these are the reactions. So why alkenes are getting formed? That is due to dehydration, not due to dehydrogenation. That is due to dehydration. So tertiary alcohol will be preferring dehydration rather than dehydrogenation. You have to remember. So these are some of the reactions what we have discussed in the last class. Okay? Any doubts? Fine. And today whatever I am going to discuss in that, many are there, very important reactions. And as I told, when it comes to organic chemistry, a reaction with the name of a person or scientist, that will be important, no doubt. Fine. So that's what we can see in the next one, where we are going to discuss about chemical properties of phenol. Chemical properties of phenol. Now you should tell me whether phenols can easily undergo for nucleophilic substitution or electrophilic substitution. Question is very simple. Whether phenols can easily undergo for nucleophilic substitution or electrophilic substitution reaction. Which one it can easily show? So it has to easily undergo for electrophilic substitution. Why? Because OH group attached to the benzene ring, it will show the positive resonance. If you recollect, based on the resonance which we have studied, if OH group is there, which will have the positive resonance, it will show positive resonance effect. So due to that, what will happen? There will be electron density at ortho and para position. So therefore, electrophiles means electron deficient species. They can attack at these positions easily. But when I am talking about nucleophiles, so it will be difficult because already electron densities are there. If at all they are attacking, they will prefer to go for meta position. They will prefer to go for meta position. Therefore, phenols, especially OH group, they are ortho and para directing when it comes to electrophiles, and they are meta directing when it comes to nucleophiles. Whether I am clear? But nucleophilic substitution, it is less preferable compared to electrophilic. So whether I am clear? All of you have understood? Any doubts? So what I am telling here is, when it comes to electrophiles, phenols can easily show the electrophilic substitution reaction, no doubt. So what is the reason? Reason is due to the positive resonance effect, right? So now what will happen due to the positive resonance? So it will lead to the more of electron density around the ring, especially ortho and para position. So therefore, whenever electrophiles are there, phenols will act as ortho and para directing molecule. But when it comes to nucleophiles, it will act as meta directing, because only at meta position electron densities are not there, right? But still, preference wise, it will easily go for electrophilic substitution reaction. Now, as we have seen, nitration can be one of the example for electrophilic substitution reaction. Now, please remember, whenever nitration is happening, we have to go with one particular combination. Which is that?
HNO3 and H2SO4.
That is HNO3 and H2SO4, right? Don't write anything. We have to go with HNO3, sulfuric acid and HNO3 in combination, right? Then it can easily undergo for electrophilic substitution reaction, that is nitration. So due to the formation of nitronium ion, in combination they will form nitronium ion, right? That is the general method, right? ಆದರೆ now you should remember, when we are talking about phenols, since positive resonance effect is there, OH is highly efficient in showing the positive resonance. So therefore, there is no requirement of sulfuric acid. Please remember, there is no requirement of sulfuric acid. Even if you use dilute HNO3, reaction will happen. But only thing is, we are going to get mono-substituted product. In the presence of dilute HNO3. Naturally, we are going to get two products. One will be major and another one will be minor. Right? Only one position NO2 group will be attached. That's why it is called as mono-substituted. So what is this? This is nothing but para-nitrophenol. And this is ortho-nitrophenol. Common name. If you want to go with IUPAC name, it should be 4-nitrophenol. And here it should be 2-nitrophenol. So that's where we have the product. Now all of us we know para-substituted product will be a major product and ortho-substituted product will be minor product. What is the reason? Because they are close to each other. With respect to ortho, it will be close to each other. That's where we have the major and minor product. But when it comes to nitration, equally it will be formed. Almost equally it will be formed. Okay? So that's where we have the two products. Para-nitrophenol and ortho-nitrophenol. Almost equal amount will be formed, but still. So we have the two products. Now when I am talking about these two, it can be easily separable also. They can be easily separable also. For example, if I take ortho-nitrophenol, now when it comes to ortho-nitrophenol, what will happen? So due to the presence of oxygen and hydrogen close to each other, they will have the affinity. They can easily form hydrogen bond with each other. That's where we have intramolecular. Please remember, this is nothing but intramolecular hydrogen bond. But when I am talking about para-substituted, right? So that's where we have the NO2. They can make the bonding with neighboring molecule. That's where we have the intermolecular. So intramolecular and intermolecular. So that's where we have the intramolecular and intermolecular hydrogen. So due to the presence of intra and intermolecular hydrogen bond, they can be easily separable because they differ from each other with respect to melting point or with respect to that boiling point. What is the reason? Intramolecular hydrogen bond will lead to lower boiling point or lower melting point for orthonitrophenol. Due to the presence of intermolecular, it will lead to the higher boiling point or higher melting point. Whether I am clear? So why orthonitrophenol and paranitrophenol can be easily separable? That is due to their difference in their melting and boiling points. Now why they differ? So normally they differ from each other, but here they differ from each other with larger value. What is the reason? The reason is that is because due to the intermolecular hydrogen bond and intramolecular hydrogen bond. All of you have understood? But one thing you should be remembering here, when it comes to nitration with respect to the phenol, dilute HNO3 can easily give rise to monosubstituted phenol. It can easily form monosubstituted phenol. Whether I am clear? There is no requirement of sulfuric acid. But generally, for nitration, if anyone asks you, if I want to go for nitration for an aromatic compound, then easily you can tell H2SO4, HNO3 as a combination. But since here we have OH, which will show efficiently positive resonance effect, so therefore even with dilute HNO3, in the absence of sulfuric acid, they can easily undergo for nitration reaction. All of you have understood? Fine. So that's where even paranitrophenol and orthonitrophenol can be separated from each other due to difference in their physical properties. Right? So that's where we have the monosubstituted product. Any doubts? Don't ever write sulfuric acid here, because my student, they remember whatever Raghavendra sir has told, that is H2SO4 and HNO3. They will forget this one. Right? You people will write the answer H2SO4 and HNO3. Then teacher will not give the marks. Then you will think, oh, Raghavendra sir have put now barve. No, I am simply making joke. Fine. So that's where only HNO3 is more than enough. Fine. So if I want more than one substitution, right? This is related to monosubstituted, right? So if I want more than one substitution, then I should go for concentrated HNO3. Then I can go for concentrated HNO3. Then there will be formation of a molecule NO2, NO2 and NO2, which we have discussed earlier. And I told this is very important molecule. And they have asked the IUPAC name. Which is that molecule? It is picric acid, trinitrophenol. So this is picric acid. Where if you want to go with IUPAC name, I can tell that 2, 4, 6 trinitrophenol. 2, 4, 6 trinitrophenol. 1, 2, 3, 4, 5, 6. So 2, 4, 6 trinitrophenol. That is nothing but picric acid. Now whether picric acid should be, that's how you should analyze. Whether picric acid should be a strong acid or a weak acid. Whether picric acid should be a strong acid or a weak acid. Yes, yellow crystalline solid. Color, yellow crystalline solid. Now in that case, yes, it should be a strong acid. Yes, Manu, very good. It should be a strong acid. Why it should be a strong acid? Why it should be a strong acid? Can any one of you, why it should be a strong acid? Already I have explained why it should be a strong acid. That is because presence of electron withdrawing groups. Due to the presence of electron withdrawing groups, right? So which will put a stress on oxygen. So due to that, oxygen will take up the electron from hydrogen and it will release it as H plus. So therefore picric acid is a bit strong acid due to the presence of electron withdrawing groups. Fine. So that's where we have the picric acid, trinitrophenol. So how to prepare trinitrophenol? Phenol with concentrated HNO. But normally when it comes to preparation of picric acid, instead of treating it with concentrated HNO3 directly, first they will treat with the sulfuric acid. Now what will happen? There will be OH, SO3H and SO3H as an intermediate. Right? Disulfonic acid, intermediate. Now phenol, OH group will lose its importance because sulfonic acid is there. We have to give priority to this. Right? So therefore disulfonic acid compound will be formed. Hydroxy disulfonic acid compound will be formed. And further when you treat with HNO3, then there will be formation of picric acid. Whether I am clear? When it comes to commercial preparation, they will go with this method instead of this one. So why this round off? Why not straight away? That is because with concentrated HNO3, reaction will be a bit uncontrollable. Reaction will be uncontrollable, and that is one thing. And during that process, there will be liberation of oxides of nitrogen, right, which can affect the ozone layer. There will be liberation of oxides of nitrogen. So therefore, to avoid this one, to have the controlled condition, they will go with first sulfonation, then they will go for nitration. Because the sulfonic acid, it is also an electron withdrawing group. So it will reduce the rate of the reaction. Due to the electron withdrawing group effect of sulfonic acid, it will reduce the electron withdrawing effect of this one, it will reduce the rate of the reaction. So therefore when you treat next step concentrated HNO3, due to less negative charges around the ring, reaction will happen with slower rate. So therefore it is a controllable condition. So whether I am clear? So why they will go with sulfuric acid and then why for sulfonation, then why then nitration? That is because to have the control on the reaction, one point. Second point is to avoid the liberation of oxides of nitrogen which can affect the ozone layer. Right? So these are the points why they will go this way. Anyway, this reaction is not there in your textbook. In your textbook they have given this one. And if I am right, they have mentioned this one in your textbook, not as a reaction, but they have mentioned it. It will be prepared by using sulfuric acid. Whether I am clear? So that's where we have the picric acid, one of the important molecule. IUPAC name of picric acid, many times they have asked for 1 mark. 2-3 times they have asked. Any doubts? So once again I will make it clear. So when it comes to nitration, phenols can easily undergo for nitration even if you use the dilute HNO3, no requirement of sulfuric acid. Even if you go with the dilute HNO3, mono-substituted product will be there. If I want to go for picric acid, then I can use simply concentrated HNO3, right? So no requirement of sulfuric acid. But in picric acid, commercial preparation also, please remember HNO3, H2SO4 together they are not using. First they will go with H2SO4, then they are going with HNO3. Fine? So to slow down the reaction, and anyway, there will be easily formation of nitronium ion, no doubt. In the presence of sulfuric acid, NO2 plus will be formed easily. Right? So therefore, first sulfonation, then nitration. Fine? All of you have understood? So that's where we have the picric acid. So next one, halogenation. Electrophilic substitution only. Next one is halogenation. First what we have discussed is nitration. Next one is halogenation. Now, whenever we are talking about halogenation, normally they will be using ferric halides. Ferric bromide, ferric chloride. So those type of compound normally they will use for halogenation. But when we have a molecule where we have substitution which will be showing the positive resonance like OH group. Positive resonance like OH group. This type of substitution whenever it is there, then they will not requirement of utilization of ferric chloride FeCl3 or ferric bromide. Chlorination, bromination. So these reagents are not required. Especially when it comes to the phenol. If I want to go with bromination, so what I can do is I can use bromine which is dissolved or it was taken in organic solvents like carbon disulfide or chloroform CHCl3 which is dissolved in carbon disulfide or chloroform, not bromine water. I am not talking about bromine water here. I am talking about just bromine in organic solvent, non-polar solvent like carbon disulfide or chloroform. This condition you should remember. You can expect the question. Name the product formed when bromine is treated with phenol in the presence of chloroform or carbon disulfide. Right? So it is not bromine water. So that's where we are going to get mono-substituted product. That's where we are going to get mono-substituted product. Right? So OHBl. So that's where we have the mono-substituted product. Now, what is the name of this one? This is nothing but phenol. Right? Because halogens will be used as prefix. So orthobromophenol and this one will be parabromophenol. So naturally which will be the major product? So this one should be the major product and this one should be the minor product, no doubt. That's where we have the major and minor product. And please remember there is no question of intra or intermolecular hydrogen bond because there is no oxygen, it is bromine. Right? So that's where we have the molecules orthobromophenol and parabromophenol. Naturally they differ in their physical property, no doubt. So fine. So that's where we have mono-substituted product or mono-halogen substituted reaction. So which will be done when bromine is taken in the organic solvent, non-polar organic solvent. Now, if I take same thing, means phenol with bromine, but here I am taking bromine water. Here I am taking bromine water. Okay, here I am taking bromine water. Right? So now, in the presence of bromine water, now we are going to get tri-substituted product, just like picric acid. So we are going to get OH, bromine, bromine and bromine. Tribromophenol. That is nothing but 2, 4, 6 tribromophenol. Right? So as picric acid will be having orange yellowish color. Right? Same when it comes to 2,4,6 tribromophenol, it will be white color. It will be whitish color, right? So it will get precipitated. It will be insoluble in the solution because we are taking bromine water, right? So it will be insoluble. So it will get precipitate, which will be a white precipitate, which will form a white precipitate. So that's where we have the reaction with bromine water. So tri-substituted product we are going to get, that is tribromophenol. Right? So that's where we have the difference between bromine in organic solvent, bromine water. Fine? Same as that of the nitration. Dilute HNO3, concentrated HNO3. We used to have the two different types of product. Here also. So bromine in organic solvent and bromine water. So that's where we are going to get the different products. Different types of products we are going to get. Any doubts? So all of them, they are example for electrophilic substitution reaction. All of them, whatever we have discussed, they are example for electrophilic substitution reaction. This is one done. One concept is done. Any doubts in this? Okay. So whatever I will be telling next, this is very, very important. This is nothing but very, very important concept. Similar to electrophilic substitution only. Now that is nothing but coal-base reaction. That is nothing but coal-base reaction. And sometimes they will call it as coal-base chemical reaction. Anyway, we will give the name it as coal-base. Otherwise we can call it as coal-base chemical reaction. But in your textbook they have given a coal-base reaction. Even we will go with the coal-base reaction only. Okay. So here it is one of the method for the preparation of salicylic acid. It is one of the method for the preparation of salicylic acid from phenol by using phenol. Same reaction we have discussed earlier but different condition. Right? So where we have discussed salicylic acid with respect to aspirin preparation, right? That's where salicylic acid we have utilized with respect to aspirin. But here salicylic acid will be prepared. It will not be utilized. It will be prepared from phenol. Right? So now when I am talking about preparation, naturally there will be a phenol. First we have to convert this phenol into phenoxide form, so that it can have more positive resonance due to the presence of negative charge on the oxygen. So what we will do is we will convert this one into phenoxide, sodium phenoxide. Right? So what will happen if I am making sodium phenoxide? Now due to the presence of negative charge on the oxygen, sodium is a good donor of electron, right? So more negative charges will be there. More negative in the sense +2, -2, -3 ಆ ಥರ ಅಲ್ಲ, electron density will be much more increased due to the presence of negative charge on the oxygen. So therefore, first step, we are making the stage ready. Okay, that's where we have got the sodium phenoxide. Now we are going to treat it with carbon dioxide. We are going to treat with carbon dioxide. Now if you observe, when I am talking about carbon dioxide, we can see two electronegative elements. Net dipole moment is 0, no doubt. Carbon dioxide net dipole moment is 0, and carbon is in its highest oxidation state, that is +4. And above that, electron density is less around the carbon because oxygens are there on both the sides. So therefore it can act as an electrophile. It will act as an electrophile, carbon dioxide. And due to the sodium phenoxide, already electron density has been increased at this position. Right? Now it will form, or it is going to attack ortho position, which is very near to the phenoxide. That is oxide ion ಗೆ ಹತ್ತಿರದಲ್ಲಿರೋದ್ರಿಂದ it will go and attack to that particular position. Right? So that's where we have got the intermediate. Now next, when it will be applicable for acidified condition, now there will be formation of salicylic acid. Now there will be formation of salicylic acid. acid. Right? That's where there is a formation of salicylic acid. Okay? So here you can call it as sodium salicylate. This one, sodium salicylate, but this is salicylic acid. So what is salicylic acid? Salicylic acid is nothing but 2-hydroxy benzoic acid. So that's where we have the coal-base reaction. That's where we have the coal-base reaction. Now they have not asked, but I can tell. I will ask the question. Write the reaction for preparation of aspirin. Write the reaction for preparation of aspirin from phenol. Right? Write the reaction for preparation of aspirin from phenol. Now we have to start from here. So you will get salicylic acid. Then salicylic acid will go for esterification. Right? So that's where we have this reaction. That's how we should connect 2-3 reactions with each other. That's how you should connect. Amit, what do you mean by am I there? I can see. Whatever you are texting, I can see. To whom you are asking, I don't know, but I am giving the answer. Okay? So that's where we have the phenol in presence of sodium hydroxide. Okay. In the presence of sodium hydroxide, there will be formation of sodium phenoxide as the intermediate. When it is treated with carbon dioxide, now there will be substitution of carbon dioxide at ortho position. Now later under acidic condition you will get converted into salicylic acid. You can skip this step, no problem. Directly you can add carbon dioxide and acidic condition. I think in your textbook they have given in the same way. Yes, they have given in the same way. Okay? But only thing is there will be bit temperature is required. Anyway, it's not there in your textbook. Otherwise, approximately 300 Kelvin, 300 to 320 Kelvin temperature is required. Okay? So not even 300, sorry, it will be more. You will go with 350 Kelvin. And even they will apply the 100 atmospheric pressure. 100 atmospheric pressure. Then the reaction will happen. But anyway, this condition they have not given in textbook. So you can directly go with carbon dioxide. Okay? So very important, coal-base reaction. Right? So what is the application of coal-base reaction? Due to that we are going to have the salicylic acid. What is the use of salicylic acid? It is utilized for the synthesis of very important drug called as aspirin. Right? So that's where we have the coal-base reaction. Fine? Any doubts? So please remember they are converting that one into first into phenoxide form. They will convert that one into phenoxide form so that reaction can happen easily. Okay? But at the end it should be done under acidic condition. You should provide acidic condition. Otherwise it will not be phenol, it will be phenoxide. Okay? To avoid that one you have to provide acidic condition in the last step. Okay? Now I have kept very important there only. I have not removed very important one because whatever next reaction I am going to tell, that is also very important. That is Riemann-Tiemann reaction. Very, very important. Riemann-Tiemann reaction. Okay? Riemann-Tiemann reaction. Very important. Okay? So that's very another important, like coal-base. But in coal-base reaction, we used to get salicylic acid. Here, it is involved in conversion of phenol to salicylaldehyde. Salicylaldehyde. Right? So instead of benzocarboxylic acid group, it will be aldehyde. That's where we have the salicylaldehyde. Fine? Now, this reaction where in the first step Naturally, phenol should be converted into phenoxide. Phenol should be converted into phenoxide. That will be done with sodium hydroxide. So that's where there will be formation of sodium phenoxide. Okay. So next step, or together also you can show, no problem. Next step, it will be treated with chloroform, CHCl3, chloroform. It will be treated with chloroform. Chloroform we have discussed in haloalkanes and haloarenes, some of the important compounds of halogen, organic compound. That's why we have discussed chloroform, CHCl3, right? Now it will form an unstable intermediate. It will form an unstable intermediate, that is benzyl chloride intermediate. That is nothing but benzyl chloride intermediate. So that is nothing but benzyl chloride intermediate. Fine. So it should have been shown in square bracket because it's a unstable intermediate. So immediately, since sodium hydroxide is there, immediately it will get converted into aldehyde. CHCl2 will become CHO, aldehyde, right? So that's where we have the role of sodium hydroxide. Now last step is naturally acidic condition, where we are going to get OH, CHO, that means 2-hydroxy benzaldehyde. 2-hydroxy benzaldehyde, or which can be called as salicylaldehyde. That's where we have the reaction, salicylaldehyde. So 2-hydroxy salicylaldehyde. So this is the Riemer-Tiemann reaction. Coal-based reaction it is phenol to salicylic acid. Riemer-Tiemann is reaction with conversion of phenol to salicylaldehyde. Fine, all of you have understood? So that's where we have the reaction. Don't tell me that how to convert phenol to salicylic acid. You should not write this step and next salicylaldehyde will be treated with oxidizing agent and you are going to get aldehyde which will get converted to COH. No, it's not possible because even this will get oxidized. OH group can be getting oxidized, especially when you are using strong oxidizing agent. Therefore, we cannot prepare salicylic acid as it is from salicylaldehyde due to the presence of OH group also. Okay, so that's where we have the reaction. Whether I am clear what I told, all of you have understood? So don't tell that salicylaldehyde will later converted into salicylic acid by using oxidizing agent. No, because even OH group is there, right? So even that can be oxidized. So therefore that is not possible. Better way of preparing salicylic acid is coal-based reaction only. That is nothing but coal-based reaction only. So next one I will keep as it is, or I can remove 1 week. So very important. Instead of very, very important, I will make it as very important. That is conversion of phenol to benzene. We have discussed conversion of benzene to phenol, right? Now I am talking about conversion of phenol to benzene. So that's where we have the phenol, right? Now when it is treated with zinc dust, or powder of zinc, okay? So zinc dust, so naturally there will be formation of benzene. And zinc oxide. So whatever oxygen is there, it will go with the zinc. Hydrogen will be attached to the carbon. Oxygen will go with the zinc. That's where we have got the zinc oxide. right? So that's where when phenol is treated with zinc dust, which is that product which is getting formed, benzene. That can be the question. Name the product formed when phenol is treated with zinc dust. Then, which is that one? That is benzene. One word answer. That is nothing but benzene. Okay? So all of you have understood? So now, next one I will make it as only important. Even I have removed one V also. Right? But important. So that's where we have the oxidation of OH group. That's what I told. Salicylic acid cannot be directly oxidized to salicylic acid due to the presence of OH group. Now, when phenol is treated with sodium dichromate, that is, what is sodium dichromate? You people might have used in your laboratory. Yes, Na2Cr2O7. Dichromate ion is nothing but Cr2O7 minus 2. So that's where we have one of the oxidizing agent, Na2Cr2O7, strong oxidizing agent. That also acidified because in the presence of sulfuric acid. Now there will be formation of an oxidized product, that is benzoquinone. O stands for carbonyl group, ketone group, right? So that's where we have the benzoquinone. So therefore, I will make a point here. Therefore, when you store the phenol improperly, that means when phenols are exposed to atmosphere for long time, that means many days, if you expose it to the atmosphere, there is a chance that some of the phenols will be converted into dark colored quinone derivatives. So why? Because phenol slowly it will be getting oxidized, right? So that's why there will be formation of dark colored quinone when you keep phenol for long time without closing it properly. So when it is exposed to the atmosphere, and all of us we know in the atmosphere we have the oxygen. So therefore it will lead to the oxidation of phenol, right? So why that dark color is there? That is due to formation of quinone derivatives, which will give the dark color to the solvent, that is phenol. Okay? So that's why phenol should be stored properly. Fine? So these are the chemical properties related to phenols. Any doubt? Until here, any doubt? So coal-base reaction is important. Riemann-Tiemann reaction is important. With zinc dust, it is important. Almost all the reaction, especially coal-base and Riemann-Tiemann. Many times they have asked. Right? So that's where we have the reaction. Okay? Now we'll come to some of the important alcohols. Naturally, this should be there, no doubt. Right? Alcohol. Important alcohol means ethanol should be there. But along with that we have even methanol. Right? So now when it comes to methanol, all of us we know that CH3OH is nothing but methanol, which is also called as wood spirit. Because earlier they used to prepare methanol by distillation of wood. Okay, that's why it used to be called as wood spirit. Okay, destructive distillation of wood components. That's why they will call it as wood spirit. But now we know that commercial preparation will be done in a different way. You people have discussed this one in your first PU hydrogen topic.
Synthesis gas.
Very good. Mayank told me synthesis gas or syn gas. Right? So that's where we have the combination of carbon monoxide and hydrogen. But sometimes I will make it clear. So CO and hydrogen in combination, normally it will be called even as water gas. Normally it will be called as water gas. Right? If it is in pure form. If there is a small amount of carbon dioxide, it's only extra information, don't worry. Small amount of carbon dioxide is there, then it can be called as syngas. Otherwise, if it is pure, only carbon monoxide and hydrogen, then it can be called as water gas. Okay? So, if any small amount of carbon dioxide is there, then it will be called as syngas. And all of us we know why it will be called as syngas. So, why it will be called as syngas?
It can be used to prepare lot of hydrocarbons.
Because it will be utilized to prepare the methanol, especially. It will be utilized to prepare the methanol. That's why it will be called as synthesis gas. Fine? So that's why still reaction is not done. So approximately 670 Kelvin. Okay? So around 300 atmospheric pressure. Zinc oxide and chromium trioxide combination. So these are the conditions we have to provide. Zinc oxide and chromium trioxide in the combination. That's where we have the condition. Then it will be getting converted into CH3OH. So that's where we have the reaction. That's where we have the preparation, commercial preparation of methanol or wood spirit. That's where we have the commercial preparation of methanol. Fine? All of you have understood? Right? Now, methanol is very toxic. Methanol is a very toxic molecule or solvent. Right? So, that is because this methanol, this is for biology students. So, this methanol, by chance, if you are consuming, people will die, right? Due to the mixing of this methanol with alcohol, ethanol. Ethanol can be drinkable, but in minute amount. But when it is mixed with methanol, even in small amount, then it will be a toxic. That is because this methanol, it will be acted by the enzymes in our body, which will get converted into methanoic acid. Later it will get converted into methanoic acid. First one, formaldehyde. Next it will get converted into methanoic acid. So this is toxic. Even formaldehyde, to some extent it is toxic. Even this is toxic. If you remember electron transport chain, so that's where it's going to block cytochrome oxidase. Right? So it's going to block the cell function, which is very much electron transport chain. So therefore methanol, even in small amount, is a bit toxic. A person can become blind. Nerves, tissues can be destroyed because these are some of the organs which are dependent on the electron transport chain. Fine, that's where we have the toxicity of the methanol. But still, methanol will be prepared because it's a very important organic solvent which will be utilized in the industry, in the laboratory for preparation of many other organic compounds, many of the organic reactions. Fine? Any doubts? So therefore, we have the toxicity of methanol. That is because its product, not exactly due to methanol, but since it will be metabolized to the product, that is formaldehyde and formic acid, so that's why they are a bit toxic. Any doubts? In that case, I will stop here. Tomorrow we will continue. Okay? And we are left over with alcohol, that is ethanol. Then we are left over with ethers. I think tomorrow and maximum day after tomorrow this chapter will be done. Okay? Any doubts? No doubts? Thank you. Thank you very much then. Take care. Okay? Take care. Bye. Thank you.